So this is our first lecture where we discuss an actual periodic structure and device, and it's diffraction gratings. It's the simplest of the periodic structures. It's a one-dimensional. It's periodic just in one dimension, but it has a lot of gratings and it occurs everywhere, and it's definitely worth talking about. We'll briefly review Fourier series. Then we'll talk about diffractions from gratings, and I'll step you through the derivation of the grating equation and we'll interpret what it means. Then we'll talk about the plane wave spectrum. We'll generalize that to the plane wave spectrum for cross gratings. And then we'll talk about the grating spectrometer, its sensitivity, kind of how it works. We'll talk about something called Littrow gratings, or we could word it a grating in the Littrow configuration. And then a neat one, the pattern Fanout gratings. These are the little caps you would screw on the end of your laser pointer that make shapes on the wall, and we'll describe how that works. Fourier series. This is important, and you may recall from last semester or conversations we've had this semester, the basic premise is this. We have a wave propagating through something that is periodic. The field profile takes on the same periodicity as the structure that it's in, so now the field is periodic. Any function that is periodic, according to Fourier theory, we can decompose into a Fourier series. Well, now suddenly our field is expressed as discrete packets, and these are actually plane waves propagating at different angles, as sometimes we call our spatial harmonics, sometimes we call them diffracted modes. But all of this stems out of Fourier series and is certainly worth reviewing before we dive into the math. So we start first with a one-dimensional complex Fourier series, but you'll notice in the kernel is a complex exponential. That looks very plane wave-like, and in fact that's what will happen. Each term in the Fourier series becomes a plane wave propagating at a different angle. We can generalize this, just like we've done in previous lectures, to functions that are periodic in two directions or even three, and we can write our Fourier series expansion. Now, from last semester, you may look at these and recall that these are only valid for square, rectangular type of symmetries, not hexagonal or oblique. In those cases, we need to expand our Fourier series in the directions of the reciprocal lattice vectors. And it becomes a little bit more challenging to do when they're not at 90 degrees, but these are the equations we would use when the reciprocal lattice vectors are at 90 degrees. Quick review. So we have a uniform wave traveling through some kind of dielectric object. The wave travels slower in here, so it perturbs the wavefront and retards the phase after propagating through this object. So now the field is perturbed, slightly resembling the object that perturbed it. If we have a periodic array of those objects, the field gets perturbed and comes out with a perturbation that takes on the exact same symmetry as the structure that it's in. So waves in periodic structures take on the same periodicity as the structure that is propagating through. Now, also, as we learned last semester and even talked about this semester, when the field is periodic, there's really only discrete directions that waves can propagate. Now, why is that? Well, it's because the field has to be smooth and continuous. So here what we're showing, these vertical dashed lines, those are the boundaries between the unit cells of a diffraction grating or really anything that's periodic. So if we have a wave at normal incidence, we see nice, smooth, continuous waves. It's continuous across the interface. So a wave pointing straight down here is an allowed direction. Well, let's just try some arbitrary angle. Well, if we force this to be periodic at this arbitrary angle, we can see the field is not continuous across that interface. That's not allowed. So this is not an allowed direction. Well, let's tilt it a little bit more, and suddenly we see the field is smooth and continuous across the interfaces. This is an allowed direction based on whatever periodic structure this is propagating through. So this is the qualitative sort of hand-waving argument of why there's only discrete directions for the plane waves inside a periodic structure. And it's really boundary conditions. The field has to be smooth and continuous. So let's think about the field inside a periodic structure. Remember, it actually obeys the Bloch theorem, where there's two terms. There's an amplitude term, and then there's this plane wave phase term. This plane wave phase term does not take on the symmetry of anything other than a plane wave traveling off in some arbitrary direction. It's really the amplitude envelope of that wave that takes on the same symmetry as the structure that the wave is in. So the total field is the product of the two. Well, how can we express a grating in general? We have a grating vector, so we could just say cosine k dot r. That will give us a generic unit amplitude sine wave, if you will. We multiply that by delta epsilon. So this would be the dielectric contrast of the grating. That's how much it swings. And then we would add on top of that some average dielectric constant. So it would swing by delta epsilon above and below this average dielectric constant. Well, if the amplitude takes on the same exact symmetry as the structure it's in, it makes sense then that we could express the amplitude as that function we described above times some scale factor out here that converts it from a dielectric constant to a field value. But this blue field term, or amplitude envelope, ends up becoming this. Now, we take this cosine, we separate that into two complex exponentials. We take this exponential and bring it in and combine all the exponentials, do some algebra, and what we end up with are three different terms. We get a term whose complex exponential is a plane wave traveling in the original direction. Then these other terms have plane waves traveling in different directions. Their wave vectors are our applied wave vector minus the grating vector, and the other one is the applied vector plus the grating vector. So what we have is a wave that is split now into three directions, the original direction, and then two directions on either side of that center direction. So our single wave has split into three due to the grating. Okay, so summarize up top here. A single wave has now split into three directions. Well, each of these are also inside the grating and will split into three different directions. Here's how the first one splits, the second one splits, and the third one splits. And notice now we're getting things like the applied wave vector plus 2 times the grating vector. Well, each of these will split three ways and so on, and that goes on to infinity. So this is how we summarize this. We have our applied wave vector plus or minus really an integer times our grating vectors, and that gives us the wave vectors of all of our diffracted modes inside the grating, where m is an integer from minus infinity to positive infinity. So we have the potential to really have an infinite number of plane waves traveling in all different directions. But now let's think about what happens when we have a wave incident on a grating. So let's say we have air up here, we have an incoming wave vector. Here's the transverse component, and it's continuous across the interface. However, we're entering a grating that is periodic, and in fact now we have to expand all of the possible transverse wave vectors that can exist in the grating. So for the x direction, we have the x component of our applied wave vector minus an integer times the x component of the grating vector. And that gives us all of the x components of our expansion, or all the possible wave vectors inside the grating. So this will always be a real number. However, the longitudinal component, the component pointing up and down, we get from the dispersion relation. And recall from last semester, when m gets large enough, this term becomes very large. We get a negative number here, and in fact we get an imaginary or evanescent z component. But the transverse component comes from the expansion, the longitudinal component comes from the dispersion relation. Well, now we come to the grating equation, but we start with the last equation we had on the previous slide. Well, what is the x component of the applied wave? It's k naught times the refractive index in the incident region times the sine of the angle in the incident region. What's the x component of our nth diffracted mode? It's k naught times the average refractive index in the grating region times the sine of the angle of that nth mode. And then minus mkx minus m 2 pi over lambda x. That's the x component of our grating. And we work through some algebra and we end up with our final grating equation. And this is the most general form of the grating equation I've seen, but I like starting here, and it has everything that can affect our diffraction. The refractive index, wherever it is we're interested in looking at the diffracted modes, the angles of those diffracted modes, the refractive index where the applied wave is, the sine of the angle of the applied wave, minus an integer m, that's the order of diffraction. We have this free space wavelength divided by the period of the grating times the sine of the slant of the grating at angle phi. And in a lot of formulations you'll find in the literature, they just assume phi is 90 degrees and make some other simplifications with refractive index. And I think you lose the full generality of what all of this can depend on. So I like this form of the grating equation. So this sort of generalizes the grating equation. I'm showing just something periodic. This could be a slab of something that's periodic. It could be periodic going all the way down. It really doesn't matter. Just somehow there was something periodic, so we had an applied wave, and this forced a periodic envelope on that. And so we diffract into multiple modes, we reflect and transmit. So we use the same grating equation to describe all of these angles on the reflected and transmitted side. The only difference is we plug in a different refractive index wherever we're interested in looking at the diffracted modes. If we're in the reflection region, we'll use the refractive index of the reflection region. If we're down here in the transmission region, we use the refractive index of the transmission region. But otherwise the equation doesn't change, it stays the same. So, and if we had more regions, we would use the refractive index wherever the region is we're interested in. Now, when we have crossed gratings, we have multiple ways that a wave can diffract. For example, if we have a square unit cell, well, there's really a one-dimensional grating heading along this direction. There's another one-dimensional grating heading along this direction. And in fact, diffraction spreads out in each of those planes. And eventually, we even get diffraction along the diagonal, and we really get a rectangular fan-out of diffracted modes. And we'll see that in a few more slides. If it's oblique, the planes of the diffraction just become oblique. Hexagonal, the planes of diffraction, there's actually 3 gratings here. There's one going left to right, one kind of going in this orientation, and then the other in the opposite orientation. So we have 3 planes that we can diffract in. And again, there's sort of this mesh grid or fan out of diffracted modes, but those are the primary diffraction planes. So here's a summary of what happens to the diffracted modes as we stretch the grating period. When the grating period is very, very short relative to the wavelength, we're all the way on the left. The grating period is so short there that the wave can't really interact with the grating, and it really just sees an average refractive index in the grating. And this is actually the next lecture we'll have. We'll talk about sub-wavelength gratings because there's still interesting stuff that happens here. But let's stretch the grating to a longer period. What happens is at some critical period, suddenly we're going to get a diffracted mode on the transmitted side. And why the transmitted side first? Because the way I've drawn it, it has a higher refractive index. And so as soon as these modes appear, they actually appear parallel to the interface. And as we stretch the grating, they swing downward. And at some point, there's a new diffracted mode. That swings downward, then another diffracted mode. And then at some point, we also get a diffracted mode on the top, and it also starts parallel to the interface. And as we stretch the grating, it bends inward, and eventually we get more diffracted modes. And so the longer the grating, the more these diffracted modes we have. And at some point, when the grating's so long, this really just tends to look like a continuous spectrum of possible angles. But in principle, it's still discrete directions. Let's look at an animation of this. And so what we're starting with is a diffraction grating that is so sub-wavelength it's not diffracting. And what's going to happen in this movie is we are animating as the grating's being stretched, and we're visualizing the diffracted modes. So it's getting longer, longer. All of a sudden there's diffracted modes on the transmitted side and more. Then they appear on the reflected side. They appear on the transmitted side here first because the refractive index is higher. If the refractive index were higher on the reflection side, we'd see diffraction modes there first. So let's play this one more time. But when it's sub-wavelength, there are no diffracted modes. Suddenly there's a very special wavelength or period where we get diffracted modes, and we can calculate what those are. Those are cutoff conditions. And some interesting things happen at those cutoffs. Suddenly there has to be a transfer of energy from the old diffracted modes to these new diffracted modes that have suddenly come alive. And we see a rather rapid transition of that energy that are called Rayleigh anomalies. This is the same movie now, but now we're coming in at an angle of incidence. And what you can see is that the diffraction is a little bit asymmetric. It's asymmetric because we're coming in at an angle and have destroyed the symmetry that we had on the previous slide. So what you'll see is diffracted modes sort of come alive on one side and then the other. It's not a symmetric diffraction anymore. It's very similar. As soon as there exists a diffracted mode, it's parallel to the surface, and as we stretch the grating, it swoops downward towards the zero order. I'll play this one more time. Again, it's the same movie, just now we're coming in at an angle of incidence. There's still a point where the period is so short that we don't get diffraction, and it's a sub-wavelength grating. That'll be the topic of next lecture. So in this lecture, we really can assume there's always diffracted modes. So how do we know when a particular mode gets cut off? Well, we know from the grating equation that we can calculate its angle. Well, when the angle becomes an imaginary number, that really doesn't make sense. What that's telling us is suddenly that mode is evanescent, it is cut off. So we can calculate the cutoff angle. We just solve our grating equation for normal incidence, so sine of 0 degrees, that term cancels off, and our grating equation reduces to this for normal incidence. Now if we want to figure out where our plus n minus 1 order modes go, or where their cutoff is, we set m to 1, and if this is an air, we would set our refractive index to 1. So we really just have sine of our theta equals lambda naught, or free space wavelength, over the period. So here's our cutoff condition. And in order for this angle to be a real number and not imaginary, this term has to be less than 1. So the conclusion is that the period of the grating has to be greater than the wavelength. And here we put refractive index back into it. So as soon as the period is greater than a wavelength, we diffract. When the period is less than a wavelength, it does not diffract. And in this case, refractive index is the average refractive index wherever it is we're observing the field, which doesn't have to be in the grating. It can be reflected from the grating. So what about total number of modes given some grating period? We know long periods diffract into a whole bunch of different modes. Again, for simplicity, let's assume normal incidence. So assuming normal incidence, our grating equation reduces to this. We want to figure out what are the conditions that keeps this angle real. So that would mean this argument has to be less than 1. Well, now we can figure out what the maximum diffracted order is that leads to that. Since we have normal incidence, our diffraction is symmetric, so we will get minus this number up to positive that number in terms of the orders of diffraction. And if we add all that up, here's the number of diffracted modes we'll have as a function of grating period. Now clearly, as grating period grows, we get more and more diffracted modes. Now, if you use this equation directly, you'll get fractions. You'll get 6.5 diffracted modes. What that really means is it's 6 diffracted modes. We round down. The half one doesn't really count. So all this comes out of the grating equation. So here's a summary, really, of how we determine all the grating cutoff conditions. So the zero order mode, that always exists. That's never cut off. And next lecture, when we talk about sub-wavelength gratings, we're really talking about what happens to that zero order mode, because some interesting things do happen to that. Well, let's say we want to be a sub-wavelength grating. We do not want any diffracted modes. So we have a cutoff condition saying no first order modes. Well, what we look for is a grating period that is shorter than what causes the angles for those first order modes to be 90 degrees. So in this case, we actually want this to be an imaginary number. And so whatever grating period would cause this angle to be exactly 90 degrees, we want to be shorter than that to make sure that we've cut off our first order modes. Likewise, if we want to make sure that we have first order modes, we would calculate that same grading period, but then say our actual grading period needs to be larger than that. Then we would be ensured to have first order modes. Well, let's say we want first order modes, but we do not want second order modes. Well, then we figure out what is the grading period so that the angles of those second order modes is exactly 90 degrees. If we don't want those, our grading period has to be shorter than that. If we do want it, our grading period has to be larger than that. Well, we can generalize that, and we can figure out what period our gratings need to be to ensure that we don't or do have certain diffracted modes. Now, what we don't have the option of is saying we want a third order diffracted mode, but not the second. That's not possible. We have to have up to some order mode, but we have all of the lower order modes. Now, what still can be done, we can optimize the pattern of the grating so that if we don't want those diffracted modes, we just don't put any power into it. After the wave passes through the grating, it only puts power into the particular mode that you're interested in. So the grating equation really just tells you the possible angles of the diffracted modes. We need to go to Maxwell's equations to figure out the amplitudes of those modes. So I like to think of gratings really happening in three regimes, if you will. So we have Bragg gratings, which are the shortest period gratings, and that's what couples waves traveling in opposite directions. And so we can operate a grating this way in the Bragg regime. We can also think about gratings as being diffraction gratings. Incoming waves diffracts the waves in all different directions, and this tends to be more of a medium period grating. We can also play with gains with waves traveling in the same direction. Those are our long period gratings, as we've discussed in our couple mode theory lectures. So Bragg gratings, those type of effects pop up in thin film optical filters, certainly fiber optic gratings. You'll see this in filter structures for doing wavelength division multiplexing for fiber optic systems. Dielectric mirrors. Metals at optical frequencies inherently have like a 4% loss. It's different for different metals, but it's there, and we can't avoid that. But we can do better if we use dielectric mirrors, and so those tend to be the preferred things for very high power beams. Photonic crystal waveguides are based on that. On the diffraction gratings, there's a lot of applications there. Beam splitters, laser locking. We can use it as a spectrally selective mirror, and you can incorporate that into a laser for locking onto a very narrow line width. Spectrometry will pass a white light beam through a grating. It disperses into the different colors, and then we can look at the various relative amplitudes of the different colors and learn a lot about what we're sensing. So you'll see there's a lot in sensing. We can also use them for anti-reflection. We'll learn more about that. Frequency selective surfaces, grating couplers all fall into diffraction gratings. And the long period gratings, which are less common to see, but you'll see those in directional coupling and also in sensors. We talked a bit about turnaround point long period gratings, so that's an application of the long period gratings. I mentioned this before, but I think it's important enough to summarize on a slide. From the grating equation, we have a nice little simple analytical equation. We can calculate the directions of the diffracted modes. We don't know the power in the diffracted modes. In order to do that, we have to go back to Maxwell's equations. Maxwell's equations will also tell us the directions of the modes, but we know we can get that straight from the grating equation, which is usually a very useful thing. And we don't actually have to resort to Maxwell's equations. But if we want to start controlling the polarization of the diffracted modes, or how much power goes into each of the diffracted modes, we have to go to Maxwell's equations and start tailoring the pattern within the grating unit cell. But just knowing the outline, the symmetry of the grating unit cell, we can calculate all of the directions of the diffracted modes. So for diffraction gratings, well, there's a lot of applications. Sub-wavelength gratings, we'll learn next time, we can use as artificial wave plates and some other neat things. Polarizers, anti-reflection coatings, effective index media, that comes from some sub-wavelength gratings. When it's diffracting, there's a neat thing called a Littrow grating, and here we design the angle of one of the diffracted modes to match the angle of the incoming wave, and we use it as a spectrally selective mirror. We'll talk more about Littrow gratings later, but that's been used to lock lasers and do a number of other things. So you'll see that in sensors and lasers. Then there's the image forming fan-out gratings, if you will. We diffract into thousands of modes. We control the relative amplitudes of what's in those modes, and we screw something on the end of a laser pointer, and out comes a shape. So there's a rabbit in a box. But really, we can generate whatever images we want. And we'll talk about that at the end of this lecture. And we can design those with an algorithm called the Gerchberg-Saxton. Holograms are stored in gratings, so holograms are kind of neat, forms these three-dimensional things that we like to see. And probably one of the bigger ones for gratings is spectrometry, where we'll have a grating, we've passed light through some sample that we've interrogated with a broad spectrum of light. We disperse that with a diffraction grating, and now we can detect all the different colors separately and learn something about our sample. Okay, on to the plane wave spectrum. So let's talk about the origin of this plane wave spectrum. So we have a wave. It is propagating through something that is periodic. The field takes on the same periodicity as whatever it is in. That field profile then, since it's periodic, we can decompose into a Fourier series, and each term in the Fourier series becomes a separate plane wave. This set or family of plane waves we call the plane wave spectrum, or diffracted modes, spatial harmonics, etc. So we start off looking at this with the Bloch theorem. And remember, the field we can write as two parts, this amplitude term and this plane wave phase tilt term, if you will. It's the amplitude term that takes on the same periodicity as the field that it's in. So we'll take this complex exponential to the left, and we expand this into a complex Fourier series. So this is just a simple complex Fourier series of this periodic function A. And this capital S, those are the amplitude coefficients of the Fourier series. And it's a function of y because we're only Fourier transforming here in the x direction, which is this direction, back and forth, left and right. Okay, so here's where we were on the last slide. We know when we now are inside of a grating, we know that we have this transverse wave vector as an expansion with integer m. So we have the x component of this applied wave, or the Bloch wave vector, if you will, minus an integer combination of 2 pi over lambda x. So we have this typical expansion in the transverse wave vector. So we can then put this inside of our complex exponential. We bring our beta in here and express this as k sub xm. So now this is where we are. But we can bring these two together now and think of it as just as a k dot r, because here we have a kx times an x, ky times a y. That looks like a dot product. Really, this has the form of a bunch of plane waves traveling at different angles, and they have some unique amplitude. This is the plane wave spectrum. Those are our diffracted modes. Those are our spatial harmonics. And in principle, if we added up all of these waves, we would reconstruct the field profile that we derived the waves from to begin with. So here's our plane wave spectrum. The field travels through something that's periodic, takes on the same periodicity as the structure that it's in. The field's now periodic. It expands into a Fourier series. Each term in the Fourier series becomes its own plane wave. And so we can think of any time we have a periodic field as it also being the sum of a bunch of plane waves at different angles. So that's the plane wave spectrum. Now let's think about the longitudinal components. We know that the transverse components of all of those diffracted modes, it's an infinite expansion. And so I've repeated that here. We get this infinite expansion. But the longitudinal component comes from the dispersion relation. And so if we solve that for the longitudinal component, we get the square root of the difference of two numbers. Well, now that we have the difference of two numbers under a square root, we have the potential for what's being under that square root to be positive or negative. So So in other words, the longitudinal component will come out either being purely real or purely imaginary. The transverse component of those diffracted modes will always be real. It's the longitudinal component that can become imaginary or real. If it's real, it's a plane wave like we always imagine. If it's imaginary, it still transports power in the x direction, but it becomes evanescent in the longitudinal direction. And we'd call that a cutoff mode. So here's how I like to visualize it. We have an incoming wave. Because it hits something that's periodic, the transverse component is this infinite expansion. In fact, it goes off to infinity to the right and to the left, but I'm not showing that. I'm only showing the 11 lowest order transverse wave vector components. But this is an infinite expansion, and they get bigger and bigger and bigger as we go left or right. Now, each one of these has to be phase matched into our grating. And depending what the refractive index is, at some point, these transverse components become so large that the longitudinal component becomes imaginary. And in fact, it's usually only the lowest order diffracted modes that are actually waves propagating in the grating. The rest are cut off, and we see the field confined to the surface. So these are our cutoff modes, where the transverse component of the wave vector has become too large to be supported in that material, and that wave becomes cut off. But notice that there is a field. We do penetrate and get some energy into that second material. It's just that it's cut off and it will be reflected. Conclusions from all this. Fields take on the same periodicity as the media that they're in. Periodic functions can be expanded into a Fourier series. Each term in the Fourier series represents a separate plane wave or spatial harmonic. There's an infinite number of terms in a Fourier series. So there's really an infinite number of spatial harmonics. It's just that power usually only ends up in the lower order harmonics, not the higher orders. So, and when we numerically solve things, we clearly only retain a few of the lower order harmonics. And it's only those that can transport energy away from the device. But those cutoff modes are important within the device, telling you how things will behave. Now I want to generalize this to look at a plane wave spectrum coming from crossed gratings. Some terminology first. We have first what are sometimes called one-dimensional gratings or ruled gratings. And from what you'll recall last semester, that required a two-dimensional simulation. Then we have crossed gratings. These are periodic in two different directions, sometimes called a 2D grating or a crossed grating. This requires a full three-dimensional simulation. So very often you'll hear people just talk about a 1D grating. It's called 1D because it's periodic only in one dimension and described by one grating vector. A 2D grating is periodic in two dimensions and is described by two grating vectors. So if we have a crossed grating, we now really have two directions that we can diffract into. So originally we had an expansion for our transverse component in X. Since now we can diffract in two directions, we also have an expansion in Y. We're going to let Z be this vertical direction, the longitudinal direction. But we still get an infinite number of KY terms and an infinite number of KX terms. Here's how I like to visualize our transverse wave vector expansions. We have the potential for a whole bunch of X component of our diffracted modes, our potential for a whole bunch of Y components, which is now still a transverse component. And if we put all these together, here's really what the transverse component of our wave vector expansion looks like. And it's these that we phase match into our grating. So when we do phase match, now we calculate the longitudinal component, and typically we'll calculate one in the reflection region and one in the transmission region. They're different because there's potentially different materials above or below the grating, so they obey a different dispersion relation. So for some material, that whatever I chose, we see that the lowest order actually give us real values for KZ. All the others are cut off, so I'm just sort of drawing these little blue lines to show you the cutoff modes. They're there, they contribute to the device's behavior, but they don't transport power in and out of the device. That only happens for these supported modes. So, upper left, here's my visualization for the transverse component of the wave vectors. This is what gets phase matched into the grating. Here's what we would calculate on the reflection side. If we put these together, here's the overall wave vectors of our reflected modes. And we can see that they're actually at different angles, but these other ones out here are cut off, and they're traveling along the surface then. And we have a similar thing on the transmitted side, so the vectors are pointing down. And here's maybe just another way I like to draw them and visualize them. What I'm not conveying here are the evanescent or cutoff fields. So, but in fact, most of them are evanescent, but I'm not drawing them here. But I like to visualize the plane waves that way. Okay, enough about diffraction gratings. Let's talk about some real devices. And our first one, and probably the most common, is the grating spectrometer. So here's what happens. We have a diffraction grating, and we hit it. We call it white light, although it's not necessarily white. It's just a broadband light. And we've passed probably through some sample. And the sample has perturbed certain colors and not others. And if we can tell what it's done, we could learn something about what we're sensing. So this broadband light that has passed through some kind of sample hits a diffraction grating, and it diffracts into some other direction. However, depending on the wavelength, that angle of the diffracted mode changes, because wavelength is a term that appears in the grating equation. So this grating disperses our different colors. So we can actually now detect the different colors separately and learn something about our sample. Let's define something that we will call the spectral sensitivity. So what this is, for two different wavelengths that we want to resolve, we'd like to send those in as different angles as possible. So we can define sensitivity as the change in the angle relative to the change in the input wavelength, and define that as the spectral sensitivity of the grating spectrometer. So we start off with the grating equation. And based on this definition, we differentiate the grating equation, and we come up with our final equation for the sensitivity, or how much it will disperse the different wavelengths. And so perhaps the more useful formula is this. We look at a change in angle given a change in wavelength. But it's from this that we can figure out how to maximize how much these two wavelengths get dispersed. We want the angle between these two wavelengths to be as much as possible. We want it to disperse. So we look at the equation, figure out how to do that. Well, m, the order of diffractions in the numerator, we want that big. So we want to diffract into higher order modes. Well, in contradiction to that is the next one. The grating period is in the denominator. So in order to make the sensitivity big, we want that small. Well, in order to diffract into higher order modes, we need a long period grating. So those two contradict each other a little bit. The average refractive index is in the denominator. We want that small, so we want to diffract into air. The cosine theta m, we want that small, which means we want the angle large. We want to diffract into large angles. So we want to use large angles. Here is a pretty good grating spectrometer. This is offered by Ocean Optics, and they have this nice picture of what is inside. And so this is a fiber optic spectrometer. So we have light coming out of a fiber, and we want to look at the spectral content of that. So they have a fiber optic input here and an optional filter. But the initial light is drawn as white light. So it hits a collimating mirror. And then on 5, here's the actual grating. So you start to see this rainbow effect symbolizing where it actually diffracts and disperses the white light. And then it hits a collimating mirror, eventually fans out and hits a detector array, so we can measure these different colors independently. And so there's an actual device, and sold by Ocean Optics using a grating. Littrow gratings, or gratings used in the Littrow configuration. What that is, we have an incoming wave, shown in green, and we will choose a grating period and parameters of the grating such that the +1 order mode comes out in the same direction as the incident wave. Now what we've made here is a spectrally selective mirror because this condition will only be matched at a single wavelength. We change wavelength or change frequency a little bit, the angle of this +1 order mode will be different than the incident wave. And so if we back up far enough from the grating, we've made a spectrally selective mirror. And when the +1 order is in the same direction as the applied wave, that's the Littrow configuration. So how do we design that? Well, we start with the grating equation. The Littrow configuration occurs when the angle of our +1 order mode equals our angle of incidence. We want those to be the same. And we have this sign difference here because the incoming waves coming from top down and the reflected waves are from the bottom up. So we just resolve the sign with a minus sign here. But that's our condition. So we can replace theta sub m with theta ints in this equation here and also put in the sign. We work through the math. This is our condition. And as long as this equation is satisfied, we are operating that grating in the Littrow configuration. We can define the spectral selectivity of this, similar to how we did the sensitivity of the grating before, but maybe we define our spectral selectivity is how much the wavelength changes given a change in angle. And so we differentiate the grating equation, and this is where we end up. And we can use these equations to estimate the bandwidth of our Littrow grating filter. We're using it as a spectral filter, and we can calculate our line width or frequency bandwidth. And so I have an example of this following. So here's a design example. Design a metallic grating in air that will operate in the Littrow configuration. It will operate at 10 gigahertz at an incoming angle of 45 degrees. Well, right away we said it's in air, so the refractive index is 1, the angle of incidence is 45 degrees, and we're given the frequency at 10 gigahertz, so we know the free space wavelength is 3 centimeters. Well, now we have our equation for the conditions for our Littrow grating. We can calculate what the period needs to be, and it turns out the period needs to be 2.12 centimeters. So if we have a metal grating with period 2.12 centimeters, and we have an incoming wave at 45 degrees, the +1 order mode will be diffracted in that same direction at 45 degrees. So let's say we have a detector that will detect about a 5-degree cone of angle. So we'll say we have this 5-degree cone where we can say it's essentially the same direction as the applied wave. Anything outside the 5-degree cone angle will be cut off, will be filtered out. So given that delta theta, we can calculate delta F, and we would know that this particular Littrow grating would give us a frequency bandwidth of 0.87 gigahertz. And of course, once we know that, we can calculate fractional bandwidth and other things that might be meaningful. Our last topic is a fun one, pattern fan-out gratings. Before we get into what is a pattern fan-out grating, let's touch on this topic. So, if we know the field profile within a plane, and this field will propagate left to right, if we go very, very far, and we look at the field profile very, very far away, what we see is that the field very far away becomes the Fourier transform of the field here. So as a wave propagates very far from near field to far field, we'll say, it essentially is a Fourier transform. We can predict what that far field would look like based on the Fourier transform of the near field. So propagation over a long distance, we get a Fourier transform. So let's say we want to screw something onto the end of a laser pointer that creates some image. And here's the UTEP pickaxe. Well, how do we do that? Well, if propagating from the near field to the far field does a Fourier transform, then we want our Fourier transform to look like a pickaxe. So really, we start with a pickaxe, calculate the inverse Fourier transform, and right here, on the outside of whatever this device is, right here, we want the field profile to take on the inverse Fourier transform of our image. So whatever this device is has to take as an input a standard laser beam, impart on it somehow the inverse Fourier transform of an image, which then would be here, such that when it propagates from the near to the far field, it takes a Fourier transform and we get our image. So that is a pattern fan out. And essentially what's happening, we have a diffraction grating that diffraction to thousands of modes, and we are simultaneously controlling how much power goes into each of those. So two ways of thinking about it, but it's the same thing in the end. These are designed, well, I guess there's multiple ways to design these. A really good way and a simple way is something called the Gerchberg-Saxton Algorithm. And here's how we start it. We start in the far field. And we know we want our field to look like this. We don't really care what the phase of our light is, but we want the amplitude profile to look like our image. And in this case, it's a pickaxe. Well, what do we do next? Now we want to figure out what the near field needs to look like. So we take the inverse Fourier transform of that, and we end up with something that looks kind of crazy. It's got a crazy phase, and it has this crazy amplitude. We are looking at the inverse Fourier transform of a pickaxe in this case. Well, usually we want these things, this grating etched in glass. When we have a grating in glass, the amplitude does not change propagating through it, only its phase. However, using this, it requires this certain amplitude profile. Well, we want transmission everywhere, so this amplitude profile will not work for us. We know we can do whatever we want to with phase, but we need sort of an all pass. It's just a piece of glass, so we need complete transmission in the amplitude. So what do? We retain the phase we've just calculated, but we replace the amplitude portion with all ones. It's an all pass. So this is something we could realize. It probably doesn't make a pickaxe yet, but what would that make? Well, we can figure that out by Fourier transforming that. And this is what it would make. It's starting to make a pickaxe, but it's an outline of a pickaxe. And it has crazy phase. We don't care what the phase is because our eyes don't see that. So what's the next step? Well, our next step is we retain the phase, but we take our ugly pickaxe picture, or what was ugly on the other slide, and replace it with our perfect pickaxe. But we keep the phase that we just calculated. Well, what kind of diffraction grating would form this? We inverse Fourier transform it, and now we have a modified phase. We also have an amplitude profile that we know we really can't realize too well. So we replace the amplitude with all ones, but retain the phase. This is something we could realize. We Fourier transform that, and what we see is our pickaxe is starting to look a little bit better. It's filling in. And the phase we don't care about because we don't see phase. Well, we retain the phase, we replace the amplitude portion with our perfect image, keeping this second phase now, and we inverse Fourier transform it and replace the amplitude portion, and we iterate this many, many times, and eventually this converges. And we end up with something like here, where we have a nice filled-in pickaxe, phase we don't care because we don't see that, and we have, all ones in the amplitude so we can pass through glass, and we have this weird phase profile. Somehow we have to do this. We have to have a piece of glass etched in some way so that when a light beam passes through it, it imparts that phase on it. Well, how do we do that? So we start with our phase, and we etch glass. So where we've etched, the light, when it propagates through that, won't see as much glass, and it actually comes out with advanced phase. Where we see mountains on here, the light will be traveling through more glass and traveling slower, and we're imparting phase. And we essentially etch this to the depth that we would get 90-degree phase out of that, and so we can convert our phase profile into an actual profile that we can etch into glass. Then if we pass a laser pointer through that, and this is just one little unit cell, we would actually repeat this over the diffractive optical element. We shine a laser pointer through that, and we get a pickaxe image. And that's how those pattern fan-outs work. and how they're designed.